Hello and welcome. This begins the subpart of specifically a series of 4 subnetting videos. So this is still continuing our network basis class, and this specific part is about subnetting. By now you know the basic format with the objectives, why do you need it, exercises, learning verification, and summary. So we will jump right into our learning objectives. So if you go through this training, you should be able to understand what is the purpose of subnetting, what does it mean to borrow bits from the host portion of the address, what are address classes, how can class A, B, and C addresses be recognized by the first few bits of the addresses, what are the default classful masks? What does CIDR mean? In the VLSM table, that's variable length subnet mask table, the number of addresses does not look correct. Why? That's the important question we cover today. Does subnetting represent a departure from classful addressing? What is Proxy ARP? So we begin. Why do you need it? Okay, going to explain. It'll take about 4 slides. See, the original view of the internet was basically 2 levels. At the top level was the internet as a whole, and then below that were all the individual networks, and each network would get its own number. Now, so it was important that, you know, the internet itself wasn't actually hierarchical, but it was possible to interpret the addresses as having a hierarchy, which is not quite the same. Now, in the old days of networking, a single cable supplied the network, and stations would actually connect to that particular cable, and the stations on that particular cable would be on the same network. Now, in some cases, networks had to use 3 levels, where the 3rd level will accommodate the multiple cables within that network. Now, so this still goes into the question of, okay, how is this related to subnetting? Well, if you recall that basically in the setup, each cable will have a different network number. So now the question becomes, how do we handle hosts that had more than one LAN? For example, you have a massive university network, so you're not going to be able to put all the hosts on one cable. You might have to use more than one cable. So how can I handle the addressing of these hosts? Well, because if you don't use subnets, option number 1, don't use subnets, that means you're going to have to use a separate network for each cable. What if you don't want to do that? What if that creates scalability issues? You're going to have a lot of networks. Actually, a lot of waste also. Now, you could try the second option, which is transparent subnets. In this case, you'll have a single network number for the entire organizations, and you just give the hosts their own numbers without regard to the LAN they're sitting on. Now, this would mean you don't actually do anything to modify the hosts, and you only make a modification at the network layer to accommodate the hosts, and the network layer handles that complexity. The next option, and what's the one that was actually chosen, was explicit subnets. And this is, you can have a single network number, but you can partition it yourself by assigning subnet numbers to the LANs. Now, there were certain disadvantages of each option. If you didn't do anything and went with subnets not being used, then you're going to run into scalability issues. Because now every single cable you have in your network, you're going to need a different network number for it. So that's going to create some issues. And then if you went with the transparent subnets, they're still going to give you issues, because now there's going to be all this broadcast traffic, because these hosts will need to discover other hosts that aren't on the actual cable with them. So they're going to broadcast, and now you're going to end up having to use some sort of proxy ARP, since regular ARP just won't work in this scenario. And then there's going to be explicit subnets, which this actually required a modification to the Internet Protocol, because before you just had to give the host a number, the IP address, but now you need to also give it, this subnet mask, so now it can realize which subnet it's in. Okay, so now we're on to our exercises. Exercise 1 of 13. What is the purpose of subnetting? Well, the purpose of subnetting is to subdivide networks. Without subnetting, there could be lots of wasted IP addresses. Exercise number 2. What does it mean to borrow bits from the host portion of the address? Borrowing bits from the host portion of the address is expressed in the context of taking host bits that are provided by the default classful masks and using those bits for the subnetwork portion of the address. Exercise number 3. What are address classes? Okay, as denoted here, the address classes were originally used to denote several address types, and these are actually documented in Request for Comment 796. And there was a Class A, a Class B, and a Class C. Now, the follow-up question, exercise 4, is how can Class A, B, and C addresses be recognized by the first few bits of the addresses? Actually, it's fairly simple. The address classes are denoted by the first few reserved bits of the addresses. Like Class A, the first bit in a Class A address will be 0. The first 2 bits of a Class B address will be 1, 0. The first 3 bits of a Class C address will be 1, 1, 0. As you can see, as the 0 moves to the right, it denotes the address class. This also lends itself to you knowing the range of decimal addresses covered by a different address class. A Class A would range from 0 through 127. A Class B would range from 128 to 191. A Class C would range from 192 to 223. Now, what are the default classful masks? This is important now. The default classful masks are, for an A, you would use the /8. For the B, you would use the /16. And for the C, you will use the /24. These are most commonly seen in decimal format. For Class A would be in 255.0.0.0. For Class B, the default classful mask is 255.255.0.0. For Class C, the one you're probably most familiar with, the default classful mask is 255.255.255.0. Now, exercises number 6. What are the possible subnet masks in IPv4? Okay, this will take about 4 slides to cover, but it'll be fun once we do it. So, as we can see here, this table is an excerpt from Request for Comments 1878, and this table here shows the different CIDR. I believe CIDR will be explained later in this particular class, but it stands for Classless Interdomain Routing. Here specifically, this refers to the length of the prefix in bits, starting from the leftmost bit going towards the right. And so this column shows the decimal subnet mask value that is calculated given this CIDR notation here. This is the number of addresses, as in there are 2,048 million addresses available, and this denotes how many Class A's are available using Classful Masks. So 128 Class A's are available if you use this particular mask. Now, this shows the mask. So we'll continue to view through these. And as you can see, just looking at the chart, we will actually go into this chart in slightly more detail later to help understand how this CIDR column becomes this decimal column, because that's the part is going to be a little mysterious. And also we're going to explain where this number of addresses is coming from. Okay, so this is same thing again. I say again, this is the one you're very familiar with. Okay, now we got to 32, slide forward, because like we said before, there's 32 bits as we said in the prior lesson. So now that we turned on all 32 bits, we can't get any further than down to a single host at this point because all the bits are turned on. We're going to explain this more later, so this will be further understood. Exercise number 7, what does CIDR mean? Because we just showed it in the table, so now we should really explain that acronym. Now, CIDR stands for Classless Interdomain Routing. And the original concept behind it was they wanted to be able to make routing easier because they wanted to be able to summarize at an arbitrary bit boundary. Keep in mind that so if they didn't have a way they could summarize these networks, that means they would, by summarize mean they could accommodate multiple networks within a single notation versus having to account for each network individually. But by using this classless interdomain routing, they wouldn't have to worry about agreeing with classful addressing and masks, but they could choose their own boundaries where they felt like. Which means, if they so chose, they would not have to only use classful networks with /8 masks or /16 or /24. They can instead use any arbitrary boundary they chose to summarize these networks for routing, which would in turn decrease the size of their routing tables. So the CIDR does utilize the slash notation, like so, a slash and then a number, and this number refers to the number of bits reserved for the network prefix. And that's what you saw in that chart table shown before. Okay, this is very interesting and fun exercise. Exercise number 8, create a binary column to be matched against the CIDR and decimal columns. And this will really be a great and fun exercise. So we looked at that VLSM table, and there was a column for CIDR, and then there was another column for decimal. So we're going to just put CIDR over here and decimal over here, and we're going to put all the binary that's equivalent in the middle. And that will help us to really see that relationship. Okay, so we're working on this chart as we see here, 1 of 4, because we can only fit about 8 per page, and you know there's 32 bits to work with. So if you can see what's happening here, these different subnet masks, you always start from the left and then you keep filling the bits in going towards the right. Which means, if you're paying attention, that there's only going to be 32 possible subnet masks in IPv4. And if you're really paying attention, you're going to realize that you're going to start noticing some patterns repeat themselves if you pay attention. So, as you'll note, the /1 corresponds to this 128. The /2 corresponds to this 192. The /3 corresponds to 224. And so on, all the way until it gets all the way to 255. Keep this in mind looking at this first slide, which only covers this first octet, because we said before an octet is 8 bits. These first 8 bits here, and these are the possible masks you can get within this octet. That's important. Now let's look. Okay, now if you will notice, now we're going to the /9 through the /16, and look what happens here. This pattern should begin to look familiar. Oh, there's an error here. There is not a 2240. There is a missing period. This should be 224.0.0. And this is why it's important to know what these things are for yourself. Because if you didn't know what this was for yourself, you may blindly copy this and you may devastate a network. The equipment shouldn't even respect that value, but just in case you got happy and made your own app one day and you decided to out-program networks and you put this in there, yeah, you're going to have some unexpected results. I'll just leave it at that. But there should be a period here, and that should be a 224, continuing that same pattern that you would have seen in the previous slide. Now look at here. That's what's happening here. The same thing as we go over each one, because we're just counting the decimal value that's being generated right here. We're just counting the decimal value being generated right here. In this decimal value, and you can see there's only so many values that's going to be available because you only have these 8 bits to work with, so you can only create 8 values going in this direction. Okay, and now we finished that chart, and by now you should have noticed a pattern occurring. You should have noticed this pattern here, hopefully. That was the point behind this exercise, to see the CIDR, the binary equivalent. For example, this /25, there are 25 bits turned on here. And then this is the decimal subnet mask that matches it. And this one is /26. This is the decimal subnet mask that matches it. Like I said, there's only 32 subnet masks available in IPv4 because there's only 32 bits to work with. Now, exercise number 9 of 13. We're still looking at that VLSM table. And it says in the the variable length subnet mask table, the number of addresses does not look correct, and why? Okay, let's look at this and try to examine what's being referred to. This is referring to these columns right here. It's saying the number of addresses here is not very exact. They seem to be going exact here, and they just kind of guesstimate it. Well, the purpose of this was for planning purposes, and you'd have a rough estimate. It was not meant to give you the exact value. If you wanted the exact value for number of addresses, then it would actually be 2 raised to the power of the number of host bits. In this case, 2 raised to the 8th power equals 256. 2 raised to the 9th power equals 512. 2 raised to the 10th power equals 1024. See, 1K just looks like 1000. 2K is like 2000, but it's actually 2 to the 11 would be 2048. And if you will notice, like I said, there's only 32 bits you can play with in IPv4. Notice that there's 24 bits reserved for your network mask, and there's 8 bits left over for the host, because 24 plus 8 equals 32. Exercise number 10. Does subnetting represent a departure from classful addressing? Well, I'm glad you asked. because subnetting does represent a departure from classful addressing. But keep in mind that network administrators still often refer to classful masks and classful address types, as subnetting implies that one is breaking up networks. Note, this breaking is often from their classful defaults, but keep in mind that one can subnet on arbitrary boundaries, as that's what makes us classless in the first place. Now, exercise number 11. Can you provide pictures to better explain why we need subnetting? You know, that would probably be a good idea. So, as originally stated in the why do you need it, there were 3 solutions proposed to the problem of different networks for each cable on a network. The 3 scenarios were basically do nothing, keep things the same, transparent subnets, which relies on Proxy ARP, then the explicit subnets, where subnets are explicitly defined on the host. Now, if nothing is done, then each cable will require a separate classful network number. And as you can see in this example, this will waste a lot of IP addresses because we're not actually subnetting anything. So that means this, so are you wasting 16 million addresses? Because you're probably not going to have 16 million hosts connected over here. So you're wasting lots of addresses in this network design. Okay, this second option shows what about we did transparent subnets? So in this case, we actually have hosts that are on different cables, but to each host, they're on the same network. So it's transparent to them the fact that they're on different cables. If they're on the same network. So in this case, we could assign a subnet on the network equipment to place these hosts within the same subnet, even though they're not on the same cable. So obviously we didn't like this option either. This will create issues. Now this is the option we went for. Explicit subnets. The hosts will be assigned to their specific network. All these hosts are in their specific networks. And now we can more efficiently allocate addresses because we can put the hosts in the specific networks we need them in. As you can see here in this example, which you will be able to understand later if you don't quite yet once we get deeper into subnetting. This network here has a capacity of 32 addresses, and we actually subdivided this network with a capacity of 32 addresses into these networks with capacity for 16 addresses each. Very efficient. Exercise number 12. What is Proxy ARP? Proxy ARP is a feature whereby the router on the network can respond to ARP requests for destinations that may not be on the same physical network. ARP does not go beyond the local segment. Thus, Proxy ARP can be used to facilitate transparent subnets. As we see here, in this case, this host normally would not be able to ARP for this host on this separate cable over here because that ARP would be limited within the scope of this interface on this router. It wouldn't actually go beyond there. But because it's transparently in the same subnet, it will actually be allowed. In this case, the router may ARP on behalf of it, for example. Okay, exercise number 13. It's kind of funny, but all this information is great, but when do I get to subnetting? I'm glad you asked. Well, subnetting will be covered more in depth in the following topics. See, the purpose of this introduction was to provide some background information about what the default classful addressing is, how wasteful addressing is without subnetting, an explanation of Proxy ARP, and all of this gives you that background so that you can better comprehend why subnetting is necessary while you're looking at the following topics. And also because subnetting, if I tried to teach it all in one lesson, it could become a very long lesson, especially with the way that I teach, with maybe a little long-winded. But hopefully it's informative. Now, please note, all the prior topics, including binary, IP, ARP, etc., have been about preparing you for subnetting. That's how important subnetting is. Now, learning verification. What is the purpose of subnetting? What does it mean to borrow bits from the host portion of the address? What are address classes? How can class A, B, and C addresses be recognized by the first few bits of the addresses? What are the default classful masks? What does CIDR mean? And we're not talking about apple cider. In the VLSM table, variable length subnet mask table, the number of addresses does not look correct. Why? Does subnetting represent a departure from classful addressing? What is Proxy ARP? Okay, summary. 1 of 7. There's going to be 7 summary slides. The purpose of subnetting is to subdivide networks. Without subnetting, there could be lots of wasted IP addresses. Borrowing bits from the host portion of the address is expressed in the context of taking host bits that are provided by the default classful masks and using those bits for the subnetwork portion of the address. Now, address classes were originally used to denote several address types, A, B, and C. The associated network and host portion of these addresses was documented in RFC 796. So if we use those default classful types, as you can see, I even show here what that first bit was. In this case, for the class A was 0. For class B, the first 2 bits would be 1, 0. And for class C, the first 3 bits would be 1, 1, and 0. Note how many bits are reserved for network in each type and how much are reserved for local address or host in each type. Now, the address classes are denoted by the first few reserved bits of the addresses as shown previously. And this here shows the decimal ranges for each address class, A, B, or C. Now, there are default classful masks for each type of address. /8 for A, /16 for B, and /24 for C. I did note earlier that you may more commonly know them by their decimal equivalents, as shown here. Classless interdomain routing, CIDR, was conceived as a way to make routing easier by being able to summarize blocks of networks using an arbitrary number of bits. There will be a topic on routing. Keep that in mind. Now, CIDR is considered classless because the arbitrary number of bits would not necessarily agree with classful addressing and masks. CIDR utilizes a slash notation where the number following the slash denotes the length of the network prefix in bits. An example, /8 equals 8 bits for the network prefix. The number of addresses shown in that VLSM table is a close enough estimate of the actual number of addresses. I showed here how you could more exactly calculate what it is based on knowing the number of host bits and calculating 2 raised to the host bits power. You should automatically know the number of host bits because you know there's only 32 bits available in IPv4, and you can subtract the number of network bits from 32, and the leftover would be your number of host bits. Now, subnetting does represent a departure from classful addressing, but keep in mind that network administrators still often refer to classful masks, classful address types, because subnetting implies that one is breaking up networks. Now, this breaking is often from their classful defaults, but keep in mind that one can subnet on arbitrary boundaries, thus allowing for classless addressing as opposed to classful. Final summary slide. Let's not forget Proxy ARP. Proxy ARP is a feature whereby the router on the network can respond to ARP requests for destinations that may not be on the same physical network. Note that ARP does not go beyond the local segment. Thus, Proxy ARP can be used to facilitate transparent subnets. This concludes this demonstration. Thank you.